Hello, a great welcome to the series on machine foundations. Myself Jarajan P. So today we are at lecture 5. So here we'll discuss in detail on forced vibrations, that is undamped. So if you refer to our earlier presentations, we have been discussing in detail on free vibrations. I'm very optimistic that the discussions we had in those lectures will surely help us to sail smoothly across this presentation. So let us start discussing how we will proceed with the analysis of a single degree of freedom system that is subjected to a harmonic load. Look here, this is the conventional spring mass model wherein we have the mass m, then the stiffness is represented through as usual k parameter, then the damping c. And remember, what makes this model unique is that here we are talking about a forced vibration. So it means that the system is subjected to a harmonic load here, Pt, which varies with respect to time, that is equal to P0 into sine omega t. Remember, here, as is very clear, P0 is the amplitude of the exciting force and omega is the excitation frequency. Now, obviously, when we look into the dynamic equation of equilibrium, it can be written in the format m into u double dot plus ku is equal to pt. Remember, we are discussing on an undamped case, accordingly c will be set equal to 0. So to solve this second order differential equation, we know that from our basics in mathematics that the total response ut can be written as uc plus up, where ut is the total response and uc we call it as a complementary solution. Obviously, the complementary solution is the one wherein we need to put pt equal to 0, or it is a solution generating from a free vibration response m into u double dot plus ku is equal to 0, and up is the particular solution satisfying this differential equation. So now let us proceed to calculate the complementary as well as the particular solution, and then we will sum up these two solutions in order to obtain the total response. Okay, fine. We know from our earlier discussion that a complementary solution in this case is a solution corresponding to a free vibration, wherein we know that uc can be written as a sine omega n into t plus b into cos omega n into t. Remember that the complementary solution consisting of the terms omega n indicates that it is a property of the free vibration. And now let us assume that the particular solution is given by up is equal to g1 into sine omega t plus g2 into cos omega t. Remember, while up contains the term omega, which is the excitation frequency related to the frequency of the applied loading, the complementary solution uc, it contains the free vibration parameter, that is the natural frequency omega n. Now let us proceed to differentiate the particular solution up two times. So on differentiating first, we obtain up dot is equal to omega into g1 into cos omega t minus g2 into sine omega t. Differentiating once again, we obtain up double dot, that's the second derivative of the particular solution, is equal to minus omega square into g1 into sine omega t plus g2 into cos omega t. Obviously, this is nothing but minus omega square into this term indicates nothing but our up. Now let us substitute the values of up and up double dot, because we know that if up is a particular solution, it should satisfy our original equation, that is m into up double dot plus k into up is equal to p0 into sine omega t. Now we have evaluated the second derivative up double dot as well as we have up. Now substituting these values of this particular solution, we obtain m into minus omega square into up plus of k into up is equal to p0 into sine omega t. On solving this, we obtain the particular solution up as p0 into sine omega t divided by k into 1 minus beta square. Remember, this solution will hold good for values of beta which are not equal to 1, because when beta is equal to 1, we know that this expression turns to be infinity, or it will be unbounded. And here, remember, beta is a very important term that we will use very frequently in our subsequent analysis, and that is a frequency ratio. And this frequency ratio is defined as omega by omega n, or in other words, the frequency ratio is the ratio of excitation frequency to the natural frequency. So look here, we have the complementary solution UC, and we also have the particular solution UP, which means that UT can now be written as UC plus UP. Okay, fine. Now substituting the values of UC and UP, the total response can be written as UT is equal to A into sine of omega nt plus B into cos of omega nt. Obviously, we know that this is our transient part, plus P0 into sine omega t divided by k into 1 minus beta square. Remember, here we have two constants A and B, which need to be evaluated based on the initial conditions. So we have two conditions, that is at time t equal to 0, the displacement ut is defined as u0. Now if we substitute this initial condition into this equation, we obtain b as u0. Now to calculate a, let us differentiate this equation once to obtain u dot t is equal to a into omega n cos omega nt minus of u0 into omega n sin omega nt plus p0 into omega cos omega t divided by k into 1 minus beta square. Now let us substitute u dot t is equal to v0 in this equation in order to obtain a as v0 by omega n minus of p0 into beta divided by k into 1 minus beta square. It does mean that we obtain both the constants a and b, so that we can write down the general solution for an undamped forced vibration as ut is equal to u0 into cos omega nt plus v0 by omega n sine of omega nt minus of p0 into beta into sine of omega nt divided by k into 1 minus beta square plus p0 into sine omega t divided by k into 1 minus beta square. As you can see that this expression is too large, don't worry about it. We'll have ways to simplify it. Now let us just review this. For example, if you consider the two terms, the first two terms, you'll find that this looks as good as the solution for a free vibration. And the first two terms, it is a transient solution, as you can see. Why we call it as transient, I will discuss. And remember that this transient solution, it depends on basically the initial conditions. As you can see that here A and B are written over here, the values, and this transient solution is entirely dictated by the initial conditions. Now again, we have one more transient component, which is essentially based on the applied load. And then finally, we have a steady state solution, that is P0 into sine omega t divided by k into 1 minus beta square. Now please remember that even if the initial conditions, that is u0 if I set equal to 0 and v0 if I set equal to 0, still I have a transient component which is essentially coming out from the applied load, that is P0, right? So now let us see how to summarize this equation and how to interpret this equation more efficiently. Okay, fine. So look here. So in order to have a better understanding of the total response, here what I did is I have made two plots. The first plot, as you can see that it is nothing but the plot for the applied load, because we know that the applied load is a harmonic load, and it is described through Pt is equal to P0 into sine omega t, which tells us P0 is nothing but the amplitude of the applied harmonic load, and that the period of this applied harmonic load is nothing but T divided by 2 pi by omega, where omega, please remember, it is the excitation frequency, or it is the frequency of the applied loading. Now, if you just see the next plot, that is very important. Here what I did is, here I have plotted, as you can see, that two curves. One, as you can see, that a jagged type, zigzag type curve that indicates the total response ut. And next you can see that in red color dashed, I have plotted another curve, that is, we call it the steady state response. Okay, and this is steady state response. Obviously, it is nothing coming from P0 into sine omega t divided by k into 1 minus beta square. Now, here we have some very important conclusions to make. And please remember here that this plot of there's a total response and steady state response I made for a value of beta, that is a frequency ratio of 0.2. Now remember, the blue one is the total response and the red one is a steady state response. So what does it mean? It does mean that my transient component, that is nothing but the difference between the solid and the dashed lines. So what does it mean? It does mean that this transient component, look here, this is an undamped case. So you will find that there is a transient component to go on existing for time up to infinity. So there is a presence of transient component all throughout the vibration response. But is this academically important? No, because we know that for many of the physical systems, there will be some amount of finite damping. So because of this finite damping, so please remember our discussion on damped free vibrations. There we have seen that just because of the finite damping present in any system, the transient component will decay with the time. So if the transient component decay with the time, what does it mean? After some time, this total solution will consist of only one component, that is the steady state response component. So remember that though we have a total response, we conclude that the transient component will decay with time because of the inherent damping. So finally, the entire system response will be governed only by one component, that is the steady state response. So to summarize, the response of the system will be governed only by the steady state response, considering that any finite amount of damping will finally make the transient component to decay with time. So what does it mean? So if you neglect the first three terms in the previous slide, we come to the conclusion that the total response ut, it is just one term, that is our steady state term, which is P0 into sine omega t divided by k into 1 minus beta square. Now you will find that this equation is too simple to understand. Now this can further be simplified in a format ut is equal to ust into d into sine omega t. Let me explain what are these terms. Here ust is nothing but the static deflection defined as P0 by k. What does it mean? So ust is the deflection, static deflection of the system if the amplitude of the load P0 is applied on it. Obviously, we know that if you apply a static load of P0, the system is having a stiffness of k. It does mean it will have a static deflection of P0 by k. Now we define another important term, capital D, defined as d is equal to 1 divided by beta square. And this capital D, we call it as the dynamic magnification factor. What does it mean? So look into this equation. This ut is u, that is the amplitude multiplied by sine omega t. So this amplitude of this response is nothing but the static displacement or the static deflection multiplied by the dynamic magnification factor. So we conclude dynamic amplitude can be written as static deflection or the static displacement into capital D. What does it mean? It does mean that depending on the value of the frequency ratio, our dynamic amplitude may be same as static displacement, or it may be much less than the static displacement, or it may be much higher than the static displacement. It does mean the very important component or the factor that governs the response is the frequency ratio beta. So the system will vibrate and it will provide a larger displacement, smaller one, etc., depending only on one factor beta, implying that the excitation frequency or the frequency of the applied load is the most important factor that will dictate the response of the system. Okay, fine. So I have made some more plots for us because in dynamics, what is important is remembering equations. It is not possible for us. So it is important we digest the fundamentals and keep it with us. Okay. So if we have the fundamentals, we can apply to any other problem. Look here. Here I have plotted the response of the system ut with respect to the time t. As discussed earlier, we know that the amplitude of the response is p0 by k into 1 minus beta square. This is nothing but u static into the dynamic magnification factor capital D, right? And look here. Here t is nothing but it is the time period of the response, which is 2 pi by omega. What does it mean? It does mean that the system vibrates in phase with the applied loading. Is it correct? Because remember, this plot I have made for beta is equal to 0.2, which is less than 1. Now let us see what are the critical parameters that will decide whether the system will vibrate in phase or out of phase. So look here. So here I have plotted another curve. So here, as you can see, that on the x-axis is the frequency ratio beta, right? And on the y-axis, it is the amplitude of motion. So this is a very interesting curve to us. Now look here. So we know that when beta is less than 1, the amplitude is positive. Why? Because we know that the dynamic amplification factor capital D is 1 divided by 1 minus beta square. It does mean when beta is less than 1, the amplitude is positive. So if the amplitude is positive, amplitude multiplied by sine omega t, that is also positive, right? So which means that the system will vibrate in phase with the applied loading. Look here. Here beta is equal to 0. Here my beta equal to 1 and here beta greater than 1. So this curve I have divided into typically 3 zones. Beta less than 1 because this is my curve, this is my line corresponding to beta equal to 1 and this is beta greater than 1. So as we know, when beta equal to 0, what happens? The amplitude will be p0 by k, which is the static displacement. So means that as long as beta is less than 1, my amplitude will be always positive, which means that the response will be in phase with the applied loading. So means when the applied loading is positive, my amplitude will also be positive. Means that this will be valid only for beta less than 1. What do you mean from beta less than 1? That is my excitation frequency. That should be less than my natural frequency. Now look here. Here is another interesting observation. At beta equal to 1, what happens? Beta equal to 1. This equation tells us the amplitude will be infinity. That's why you will find that beta equal to 1 means my excitation frequency and the natural frequency are both equal, which means that the frequency ratio beta equal to 1. So we conclude here a very important fact, that is, when the excitation frequency is equal to the natural frequency, the amplitude of vibration will be infinite. Because remember, in actual practice, it will not be infinite because there will be always damping. But right now we are discussing undamped systems. Now look on the third stage, that is beta greater than 1. When beta is greater than 1, what happens? This value will be negative. That is, even when the loading is positive, the amplitude is negative. Or in other words, we can say that the system response will be out of phase with the applied loading. So that is the important conclusions we make out of these two plots. Finally, I made two more plots here. So this is a plot wherein I made a frequency ratio beta along the x-axis and the dynamic magnification factor. Remember, I have taken the absolute value of this dynamic magnification factor because we know that D can be positive, it can be negative. So here I have taken, for a better understanding, the absolute value of this dynamic magnification factor along the y-axis. So still we have some more very valuable conclusions to be made. Now we will consider, look here, I have taken for convenience only beta from 0 to 2 so that I will be able to throw some more light on our discussion. Now if beta is small, so look here, suppose that I am talking about, for example, beta from 0 to 0.2. If beta is small, what do you mean by beta small? That is, my excitation frequency will be very small. That means we are talking about the applied loading is slowly varying. When the applied loading is slowly varying, what means excitation frequency will be small, beta will be small. When beta is small, you can see that D is almost equal to 1, right? Which means that, or I can tell you that D is only slightly larger than 1.0. And accordingly, the amplitude of the response is essentially remains the same as a static one. So to conclude, for a slowly applied force, the amplitude of the response will be almost equal to the static one. What was the static displacement? It is P0 by K. So here if you look into the beta value, you'll find that at some value of beta, T is again 1 and this beta is nothing but 1.414 because we know that D is 1 divided by 1 minus a beta square, means that for beta greater than square root of 2, that is 1.414, D will be less than 1, implying that the amplitude of the response is less than the static response. Okay, so because we know that the amplitude, dynamic amplitude is the D multiplied by the static one, which means that when beta crosses the value of 1.414, the dynamic amplitude will be less than the static response. Now let us go further, beta say 3 or 4. So you'll find that this curve for larger values of beta, this curve goes on reducing, which means that for larger values of beta, what do you mean by larger value of beta? Means that we are talking about larger excitation frequency or a rapidly varying force. D will be very small. So means that whether the amplitude will be static one or it will be larger than the static one or it will be too small, everything depends on a single parameter, that's a frequency ratio beta. Or in other words, it is the excitation frequency that will govern what would be the value of the dynamic amplitude. And again, we know that at a resonance, the excitation frequency will be the natural frequency for which beta equal to 1, that is this line, and for which D will be unbounded. Here again, I have made a simple plot, another simple plot, which shows the frequency ratio beta and the phase angle theta. Remember, phase angle is nothing but the angle by which the system response lags behind the applied loading. Now, we have already discussed that as long as beta is less than 1 in the previous graph also, the amplitude is always positive, which means that for values of beta less than 1, the phase angle will be always 0. And we know that when beta crosses 1, the amplitude will be always negative, which means that for values of beta greater than 1, the system response will lag by an angle of 180 degree from the applied loading. So that's all regarding our discussion on undamped force vibrations. So thanks a lot for listening. Bye.